Hey guys, it's Andre from High Performance Academy. Welcome along to this week's webinar. Now, today we're going to dive into a little bit of information around GM idle tuning using the HP Tuners software. This is an area that I know a lot of tuners struggle with. In a factory engine, not a big deal. Generally won't even need to touch anything, but I know a lot of people really struggle when it comes to fitting, particularly a large aftermarket cam. All of a sudden, they have a huge amount of trouble getting the car to idle properly. The car will stall or it won't start properly when it's cold. All these sorts of things that really get frustrating, particularly if you're living with a car day in and day out as your daily driver. So we'll get into that once we get into our webinar. But before that, just wanted to cover off a few things that have happened since this time last week. I want to actually start with a couple of Instagrams that I put up during the week, which got a little bit of conversation going. And I just wanted to dive in a little bit deeper than it's sometimes possible to do when I am putting up these Instagrams, even with getting back to people in the comments. So we'll head across to my laptop screen for a moment, and this is a shot that we took of a test harness or a demo harness when we were at Renvale over in the UK. So you can see there is a nice little window cut in this raychem heat shrink or heat molded boot on the back of this Motorsport connector, so you can see what's going on inside. And I'll just back off a little bit here and actually just talk about Renvale briefly. So Renvale, probably not a name that a lot of us in the enthusiast market are likely to recognize, but they're a pretty big deal. They currently make the wiring harnesses for every single F1 constructor with the exception of Williams, and currently with Williams form, probably not one that they're too worried about getting onto their CV. They're also doing harnesses for WRC, superbikes, basically anything that's at the cutting edge of motorsport. They are probably likely to be producing the wiring harnesses for it. So obviously they kind of know what they're up to, and they know how to make a harness that is going to be reliable under the vigors of motorsport use. The thing that we do see quite often, which is represented in this Instagram quite nicely, is that in professional motorsport harness construction, it's pretty common to see these wiring harnesses are all built using a single color wire. So in this instance, just to probably add a little bit of color to this one, they've used yellow, although more often we're going to see that the wire used is white. Now, the reasoning behind this is that when they are producing a lot of harnesses in bulk, it makes it a lot easier if they've only got to have one color of wire available in stock, albeit obviously they've got the white wire in a range of different gauges to suit the application. So it cuts down massively on the amount of stock that they need to keep at their premises. I'll just mention actually back on this photo as well before I get roasted by people on the internet, as often happens. We can see here this opening. This, remember, is just a demo piece that Renvale produced to put on display. Normally what we would find is that the actual wires beneath the boot here will actually be covered in a gold colored tape, which is called Kapton tape. This is a thin insulating tape that is used not so much in this instance for its insulating properties, but more along the lines of, because it has a very high temperature rating, it doesn't tend to degrade or melt when the molded boot is recovered onto the back of the Motorsport connector. So what this means is that the epoxy on the inside of the boot won't end up contacting the wires, meaning that if at a later point the boot needs to be cut off and a repair needs to be effected, it makes it much easier to get the boot removed and it's not going to be stuck to the wires underneath, which I'm also just going to dive into a little bit as well before we get into the single color theme. So when I posted this up, we've had a lot of people talk about the need to actually repair these harnesses, and what we do need to understand here is that yes, a motorsport, professional motorsport wiring harness constructed in this manner using Motorsport connectors, heat molded boots, DR25 with transitions, it is pretty close to impossible to do much in the way of repairs on these sorts of harnesses. Now, there are a couple of caveats that we need to understand here. First of all, the likes of Renvale, when they are producing one of these wiring harnesses, they're produced to a very high standard. So once the harness is completed, before all of those boots are recovered into place and everything is finalized, it is run on what's referred to as a HPA tester. And this HPA tester does two things. First of all, it is programmed for the particular harness that they are testing. So what it means is instantly it will run a test on the harness and ensure that every conductor connector or terminal is in the right location. Even when you're being as careful as possible, it is possible sometimes to inadvertently get a terminal in the wrong location on one of these Autosport connectors. So that's the first test. It makes sure that the integrity, the harness, all of the conductors are going to the right location. So essentially, as long as the documentation provided to renvale is accurate, then the harness will work as expected. The other part of the HPA tester though, which is just as important, maybe even more so, is that it will then run a high voltage across all of these conductors. Very briefly, it's not going to do any damage to the conductors, but what it does is it tests for the integrity of those conductors, making sure in particular that there aren't any nicks in the insulation on a particular conductor that may allow or may result in problems with breaking down under high load later on when the harness is in service. So once it's gone through that HPA test, the manufacturers at renvale basically know that that harness is good to go and it is going to work when it's put in place. Now, in terms of repairing the harness though, at the likes of F1, the teams really aren't that worried about the cost of these harnesses, and they will actually replace, or most of the teams are replacing the entire harness after a full race weekend. So there you go, repair not really a huge concern at that sort of level. Basically, if there's a fault with the harness, the entire harness gets replaced. You're not going to find the team cutting into the middle of the harness if it's been abraded through and trying to effect a repair there. Now, moving on to the rest of that story though, again, we'll jump back to my laptop screen, and what I'll do is just show you how the single color harnesses are constructed. So renvale use a selection of colored heat shrink, which we can see here, and basically when the harness is being constructed, the little colored heat shrink pieces are placed on the end of the individual strands of wire, like you can see here. So this just identifies the wires so that the person constructing the harness knows exactly where each wire goes, making it really easy to ensure that each conductor, even though they are all white, does make it into the correct location on the harness. So not that tricky if you're doing this day in and day out, although personally when I'm constructing harnesses I still like to provide a little bit of color in there. Particularly I use a certain color for my 12 volt feeds, another one for my 5 volt sensor feeds, and another one for power grounds and sensor grounds. So this way at a glance I kind of have a pretty good idea of what I've got running in a particular area of the harness. And beyond this, of course, regardless whether you're using colored wire or all one color, documentation is the key to make it really easy when you have to come back and effect a repair or try and work out what exactly you had designed the harness, a certain area of the harness to do. It's really easy to come back and look at that documentation and then you'll know. All right, I just want to give you a bit of a rundown as well on our weekend, and we are just like everyone else out there in the motorsport industry. We love motorsport and we try to do everything right as we promote with our courses and our webinars. However, sometimes even when you do your absolute best, things just don't go to plan, and that was basically our weekend. So I thought I'll just run you through what happened, and for the first time in a long time we've actually had two race cars that are both up and running. For those who have been following us for a while on these pre-shows, you may have heard of the problems we had with our black Toyota 86 since we fitted the 6-speed TTI sequential gearbox. So for those who aren't aware of the car, just give you a really brief rundown. We'll jump across to my laptop screen for a moment. So this is a car that we ended up purchasing off one of our customers. If you're interested in learning more, check out Project Panhard, I should say, on our YouTube. There's a full build series around the wiring and tuning of this, but it is fitted with a Toyota 1UZFE 4-litre V8. Originally it was a stock engine, however the owner of the car at the time thought it really wasn't producing enough power, so it's now fitted with a fairly heavily modified 1UZFE, this time with higher compression, CNC ported heads and some pretty aggressive cams, producing around about 450 horsepower. It's also dry sumped, so that's the engine. About, I want to say maybe 4 months ago now, we fitted a 6-speed sequential gearbox into it, which on face value should be a pretty easy modification. However, since we got the car back from the fabricator, we had problems with triggering. We were seeing a lot of noise on the trigger inputs, and we basically came to the conclusion that the fabricator managed to actually fry something in the harness when he was welding to the car. Not 100% sure exactly what's gone on there. A little hard to get a specific answer. However, what we've done is constructed a new harness straight from the MoTeC ECU out to the ref and sync inputs, and this really goes to show just how important those inputs are: the engine speed or reference input and the synchronization or engine position input tell the ECU what the engine speed is and whereabouts in the engine cycle it is. If it doesn't have this information in a clean format that it can understand, then it can't calculate how much fuel to deliver, what ignition time to deliver, or when to deliver it. So we're having a lot of trouble, and unfortunately this also coincided with us being incredibly busy. However, we've got Brandon joined the team a couple of months ago. We got him onto the car just recently. He rewired that, got it up and running, wired up the strain gauge for the shifter, so this allows us to perform clutchless upshifts, and because it's a strain gauge, it tells the ECU whether we're pulling back on the sequential lever or pushing forward. So when we pull back, obviously it can produce a fuel or ignition cut for the upshift just to unload the dogs in the gearbox and allow the shift to complete. On the downshift, it will then automatically blip the drive-by-wire throttle, allowing us to automatically match revs. So just makes the driving experience a little bit more seamless. Basically takes arguably some driver skill away, but it does allow us to concentrate, particularly with the downshifting, and concentrate solely on maximizing the braking force. So we've got that going. We also have our racecraft Toyota 86, which is our original development car with a turbo FA20, and we were heading to the track, so we were pretty excited. So things started pretty poorly when we were loading up the racecraft car onto one of the trailers. This was a borrowed one, and the trailer broke just as we got it loaded up. So not to worry, we decided that Jono and Ben would drive the racecraft car through to Highlands Motorsport Park, would trailer the black 86 through, and everything would be fine. Well, everything wasn't quite fine, and about 5 minutes away from the workshop, we got a phone call, and the racecraft car had broken down on the side of the road with no fuel pressure. So this is on my laptop screen. This is the image that faced us when we pulled up behind them. To add insult to injury, while we were hoping for a pristine day at the racetrack with bright sun, winter here in Queenstown wasn't quite so kind to us. So while we were trying to diagnose on the side of the road what exactly was going on there, it actually started snowing. So obviously perfect weather to head to the racetrack. After a quick look on the side of the road, we came to the conclusion we weren't going to be able to diagnose and sort that, so we decided to carry on, and we got to the track to be faced with some pretty uninviting weather. So I'll jump across to my laptop screen again. It was pouring with rain, heaps of standing water on the track, as we can see here in the pits. We did have the car on slicks, but we had a funny feeling we were going to be faced with a bit of rain, so we did bring a full set of wets, put those on the car, and we did actually manage to head out and get a few laps in. Happy to say that the shifter, the sequential gearbox, everything was working really, really nicely, although it's a little hard to tick it off as being a job complete, because with so much rain and so much standing water on the track, even with the full slicks, it was difficult to use much more than about 50 or 60% throttle, and I don't think I saw the shift light too often. So we'll be looking forward to heading back to the track on a drier day to really put it through its paces. However, even that car didn't quite go to plan. After 2 sessions out on the track, which probably only equated to about 15 laps, I had a warning come up on the dash for low voltage, which generally means you've got something wrong with the alternator or charging system on the car. I had a quick look under the engine bay and found that the wiring to the alternator, the main positive feed off the alternator, the terminal had fractured, which put an end to our day. So not a great look, not an ideal situation, but unfortunately that is motorsport. Now this probably does bring me to a point that's worth mentioning here. If we look at the failed crimp joint here, or failed connector, it's actually not the crimp joint that's failed. What we can see is it's actually fractured right through the center. So this is where the eyelet terminal goes onto the main positive feed off the back of the alternator. Now, we're really only assuming at the moment that this is most likely going to be vibration related, and this really just is a good point of showing how much vibration can be present in a race car. The solution to fixing this is going to be probably to better support that positive feed off the alternator, making sure that it is supported so we can't get relative movement between the cable and that terminal where it goes onto the alternator. And there are a few things we can attach that to near to the alternator, so hopefully we'll get that back up and running and that's not going to be a problem in the future. But this sort of goes a little bit deeper as well as to why we talk quite passionately about keeping solder away from wiring harnesses in a motorsport application. There is a lot of vibration going on in a motorsport vehicle, and as you can see there, that's caused a failure of that particular cable. It does do exactly the same thing with soldered joints as well. You've got a lot of vibration and a lot of relative movement that's being caused by that vibration, and solder does have a habit of failing, particularly at the ends of the solder joint. So crimping there is a more reliable technique. It's not as susceptible to failure as a result of vibration. And as you can see, if we just pop back to that particular image as well, this wasn't soldered. We can see the crimp joint there. We've used a hydraulic crimper, and if you are eagle-eyed, you can actually see there's sort of a hexagonal pattern where that is crimped on. Afterwards, which has been cut off so we can effect this repair, this whole section here is insulated with some raychem SCL just to support it, and also to insulate it from shorting out on something. So the actual failure has happened at the terminal itself, where it's bent through sort of 70 or 80 degrees, and again, just vibration related. So crimping, definitely superior, but we're still going to have to do something to get around that problem with our vibration. Just wanted to talk briefly about the car that is sitting off to the side of me at the moment, still bolted up to our mainline hubdyno, and we don't do a lot of customer tuning here at HPA. We've simply got too much else on our plate producing content for our courses. However, this is a favour that we've done for a local workshop that we work quite closely with, but it was one that piqued my interest as well. So this is a Porsche 996 GT3 Cup car. If we just jump across to my laptop screen, it does have a few bits that make it a little bit unique compared to the normal Porsche 996. That's generally regarding the engine compartment, and if any of you out there are Porsche fanatics, you're probably thinking that this doesn't look like the typical Porsche engine sitting in there, and that's exactly the case. It's probably one of the more unique swaps I've heard of in a Porsche. It's got a 7-litre GM LS7 swap, so really wholeheartedly embracing the lstheworld kind of mantra. It's exactly what the owners of this car have done. They've not only fitted a Mast Motorsport LS7 into their car, they've also fitted in front of that a Hollinger 6-speed sequential transaxle, which is paddle shifted. So pretty lethal combination. This car is built for endurance racing here in New Zealand, where it competes in 3-hour endurance events. The team had previously run a Porsche engine with twin turbos and had suffered some reliability problems. So while I can't say that you couldn't get the same sort of horsepower out of a turbocharged Porsche engine, this is the way the team decided to go. So we've got that sitting there on the dyno, and I think we've got the power figures there. So I produced 616 horsepower at the hubs, running up to about 7,200 RPM. So it should be a pretty lethal combination. Also plenty of torque right through the rev range there. Now, while it was on the dyno, we've actually just filmed a little piece that will be going on our YouTube shortly, but I just wanted to talk about the way we can use the dyno when we are tuning a car like this. So for those who have joined us pretty regularly, you'll know that we have just taken delivery of our mainline hub dyno. Prior to that, we had our mainline four-wheel drive rolling road dyno. Regardless of the type of dyno, both of these dynos are what is referred to as a load-bearing dyno. So they are fitted with an eddy current power absorber. So that eddy current power absorber basically has the ability to apply a load either to the rollers or to the hubs in the case of our hub dyno to control the hub speed and in turn the engine RPM. So this allows us to perform what's referred to as steady state tuning, and for any of you who have attended one of our webinars or gone through our courses, you'll see us regularly performing steady state tuning. We quite often get asked how we can keep the RPM steady, so that's why I'm talking about this. So basically with steady state tuning we can set the dyno to hold a specific engine RPM, and then regardless what we do on the throttle, the dyno will apply more or less load to the hubs in order to control the engine RPM, hold that steady, and that allows us to access and individually tune specific sites in our fuel and our ignition table. So if we head across to our laptop screen again, we'll just go back through and get onto our fuel table. So this is the MoTeC M150 that is fitted to the Porsche 996, and we've got the graphical view of the fuel table out here on the right hand side, but what we can see, we've got a lot of numbers here on our VE table, and what I see a lot of tuners do is they'll simply jump in the car, go straight to full throttle and perform some wide open throttle ramp runs. And the problem when you're doing that is that you're only really accessing a very narrow area of the engine's operating parameters. So basically right up at wide open throttle, full load, maybe from 2000 out to 7,500 RPM, which is fine if you're tuning a drag car. Doesn't make a lot of sense to be steady state tuning a drag car, but particularly for a street car and even a circuit car, we are using quite a wide range of our fuel table, and it's important to make sure that all of the lighter load areas and transition areas of that table are accurately mapped. So particularly here, what I'm concentrating on when I'm tuning a circuit car like this is the rev range that the engine is going to be using. So obviously, yes, we will be spending a lot of time at wide open throttle. We're also going to be spending a lot of time off throttle when the driver is hard under braking, but through a corner or coming out of a corner and just gradually easing to the throttle, we are using different areas of the table. So we're trying to really optimize all of those areas using steady state tuning. So for example, I spend a lot of time between about 3,000 and about 5,500 RPM in the lighter load areas of the table, basically getting all of those individual sites dialed in. We do exactly the same for the ignition tuning, although again here with the ignition tuning being absolutely at MBT at part throttle is not really that critical. Generally I'll be a little bit conservative. The reason for this is if the driver isn't at full throttle, then the driver doesn't need or isn't asking for full power and torque. So we can be a little bit conservative with our ignition timing, but the fueling we want to be really accurate with. And this is going to result in a car that once the driver's out on the track, regardless what combination of engine RPM and throttle position they use, then the car is going to feel smooth, it's going to feel responsive, and it's going to feel crisp when the driver accelerates. The other aspect we quite often hear people complaining about is tip-in or acceleration enrichment issues. And while acceleration enrichment is another topic for another day and requires that area of the ECU is dialed in correctly, quite often what I see is people will have major problems with the base fueling in their fuel table, and then this in turn results in problems with acceleration enrichment. But instead of trying to fix the fuel table, they then try and add a band-aid onto it by fixing the problems they've got with transient response with their acceleration enrichment. So really it all comes down to make sure your fuel and ignition tables are correctly tuned first. If you do your job properly there, you're going to find that everything else just becomes a lot easier. Now I will mention here as well that steady state tuning isn't an option for every dyno. And basically I break dynos down into two types, where they have load bearing, where we have a power absorber module or some way of adding load to the car. The other type of dyno that is very popular, particularly in the US, is the inertia style dyno. And with an inertia style dyno, all we've got is a large drum or roller of a known diameter, and normally they're quite heavy as well. And basically, if the dyno software knows the diameter of the roller, the mass of the roller, then by measuring how quickly the roller is accelerated during a ramp run, the software can then calculate power and torque. Now, they are actually really good for doing wide open throttle ramp runs. They are also quite significantly cheaper because there is no power absorber or anything type of brake on the dyno. However, hopefully you can understand that there is nothing to stop the dyno accelerating, so they're not a lot of use for us when it comes to steady state tuning. Right, I also wanted to mention we have just released our newest video today, which was another one that Jono and I shot when we were over at Goodwood Festival of Speed. Loving all of the F1 content that we managed to shoot over there, and this was I think a 97 Williams F1 car, and of course the technology has moved a long way since 1997, and one of the challenges for people running these particular cars in historic or exhibition meetings is being able to actually communicate with the ECU and make tuning changes as required. So we got a chance to talk to Milan from Persis Tech, who is an ex-Cosworth employee, and he did a complete electronics retrofit on this Williams F1 car. So we talked to him about what goes into modernising a F1 car in terms of electronics. In particular with this Williams, they used a hydraulic shifted sequential gearbox, paddle shifted gearbox, and they had their own body control module. So in this instance, shift request needed to communicate from the ECU to the Williams body control module. So there was a lot of CAN decoding required in order to do this. Interesting as well that F1 were using CAN back then, or probably well before, where in the aftermarket, of course, it's only something that's become popular with the enthusiast aftermarket much more recently. Probably no big surprises there. That particular engine as well, we talk about the fact that in race trim, it produced around about 740 horsepower, running to 17,000 RPM. Obviously, with such an expensive car and an engine where it's hard to find parts or even hard to get them serviced, making maximum power is no longer the goal. So the original ECU, Milan was able to reverse engineer the fuel and ignition data out of that ECU, so had a good starting point with the Cosworth ECU, but it has been significantly detuned to the order of about 650 horsepower now, and most importantly, just dropping that rev limit from 17,400 down to about 16,000. That gives a massive improvement in the life expectancy of these engines. So if you are on our YouTube channel, check that video out. If you aren't on our YouTube channel, make sure you go and check it out. Subscribe while you're there. Give that video a thumbs up. If you've got any questions, ask them in the comments. Quite happy to jump in there and do my best to answer any questions you might have. Lastly, I also want to welcome to the HPA crew Scott, our newest videographer. Scott has just joined the team from Christchurch in New Zealand, so around about 6 hours drive up the road from us here in Queenstown. So we're excited to have another videographer on board. I know Jono's super excited because he has been drowning in workload just for the last few weeks. So hopefully with another videographer on board, we're going to be able to step up our production, and we're looking forward to getting Scott up to speed and producing some great content with him shortly. All right, thanks for watching there, guys. I will just take a short moment here and we'll get started with today's webinar. Thanks.